hopefully you had a chance to read it, but if you didn't, it's definitely worth looking over. It talks about the assessments that we have left for the term, as well as the details about the optional final. So as you read through that email that I sent, if you have any questions that come up, feel free to stop by Drop In Help or anything like that. But we are approaching the end of the term, which is very exciting. And so the big thing I want to emphasize from the email is that the optional final is on Moodle and not in Boyden. So you're still taking it on Moodle, even though on the schedule it says Boyden. If you go into Spire, nobody's going to be in Boyden. Everything's on Moodle. So if you're planning on taking it, then you would just log into Moodle during the final exam 2-hour period block. So we are covering the last chapter that we have for our course. And we started section 5.3 last time. We will work through some of it today. We will probably not finish it. So you'll notice that on Moodle that there's only one mini quiz this week on Sunday, and there's not a mini quiz tomorrow. And that's because section 5.3, which is what we're working through, is rather long. And so I didn't think we'd be able to finish it today. So there's just one mini quiz on Sunday, which will cover 5.3 and 5.4. So on Thursday, we'll do 1 or 2 last examples from 5.3, and then we'll do 5.4, which is a bit shorter. So that's sort of our plan for today. So I'm going to go ahead and switch over to the dot cam here. Hopefully. All right. So at the end of last class, we started looking at really specifically this idea of area in relation to the things that we've been talking about, right? So we talked about triangles and rectangles and how we've been using rectangles and area to really think about this area under a curve and how we were able to make it better, right, by using limits and getting the exact area under the curve. And then we brought in this idea of negative area. And so we said, okay, well, negative area has context when we are in calculus, right? So if we're computing a definite integral, we can have negative area, or if we know that the function is a derivative or a rate of change, that would give us negative area. But we need to sort of think about what it might look like if we are still trying to find area, but we don't want it to be negative. That's something we'll talk about today as well. And so we looked at some examples of when it would be negative, and that would be good for us because we have a function that would naturally give us something that we expect to be negative. And we looked at a visual representation of when area is negative and positive. We said area is positive when it's above the x-axis and it's negative when it's below the x-axis. And so we start off our discussion today with talking about what if we have both, right? So in this picture, we have both positive and negative areas. How do we deal with that? What does it mean? Is it important to have both? And what happens with calculations, right? So when it's positive for some values and negative for others, it again depends on if we are talking about it in the context of calculus with a definite integral and derivatives, or if we're just talking about general area, right? So when we talk about it in terms of calculus, we really take into account when it's positive and when it's negative and what it means, and then we add it all up. But when we do it in terms of not calculus, when we're just talking about area, we're still able to use our definite integrals to help us talk about what's happening, okay? So with example 1, what we're going to do is we're going to think about how we can talk about total area between 4 minus x squared and the x-axis for the interval 0 less than or equal to x less than or equal to 5. So this particular example is an example where we don't have a definite integral, where we are not told that the function is a derivative. And so we are truly trying to find area as though we were in, say, like a geometry class, right? How much space are we taking up? This is the way that you would see a question worded that was not using a definite integral or a derivative of any kind. So what's the approach here? So I'm going to draw a picture to help us understand how to tackle this problem, and then we'll try it. So I'm going to make that kind of long. So 4 minus x squared is a parabolic function that comes up and goes down for a long period of time, or it just goes on forever and ever. And so it crosses through at 2. And I know it crosses through at 2 because if you set this equal to 0 and solve, you can find where it crosses through. We are interested in the area that is between the x-axis and the function from 0 to 5. So from 0 to 2, we get this little semicircle situation here. And then after 2, from 2 to 5, we're finding the area that's here. Imagine this goes down forever. It is bounded into like a triangle shape. I just don't want to go into the next example, right? So we're trying to find these two areas. And the way we think about this in this context is how much space are we taking up? Well, in order to answer that question, we need to answer the question, how much positive area do we have and how much negative area do we have? And we take that negative area and we find the absolute value, which tells us how much space we're going to be taking up, right, from 2 to 5. So we'll have to count that as positive once we have that. So what do I want you to do? I want you to find the integral from 0 to 2 to find all the positive area of this function. I want you to take the integral from 2 to 5 to find all the negative area. And then I want you to think about how we use that area to talk about the general area or how much space we take up. So there's 2 integrals that have to happen here. It'll be good practice on your calculator. So I'd like you to take 2.5 minutes, set those up and calculate them and see if you can think about what we're going to do with those numbers to answer this particular question. Okay, so take 2 minutes and then we will go through it together. Okay, take about 30 more seconds. All right. So again, we need to figure out what the positive area is because that's how much space we're taking up here and how much the negative area is. So to find the positive area, we're setting up an integral from 0 to 2. That's the bounds that we see here of our function 4 minus x squared. And we throw on the dx because again, this has to match the operator that we're using here. Okay, so we plug that in and we get 5.3 repeating. So 5.33333. And that gives us the total positive area. Now, if we also set up an integral to represent the negative area, we have the integral from 2 to 5 of 4 minus x squared dx. And when we plug that into the calculator, we get negative 27 to represent this negative area. So the first question or thing we need to discuss is why can't we just do the integral from 0 to 5? If we do the integral from 0 to 5, what it's going to do is it's going to add these two numbers together, the positive plus the negative, and that'll give us something like negative 21.6. And that would represent the total change. It would sort of cancel out this amount of positive area here and leave us with just some negative area and talk about the overall impact. But this particular question is just looking for area. So how much space are we taking up? Well, in this first chunk, 1, we're taking up 5.3 units of space. And then in the blue chunk, we're taking up 27 units of space. The negative just tells us where it is. So what we have to do when we have no reason to believe that we are in any sort of calculus situation is we need to add these together in absolute value. So we need to do 5.3 plus 27. The absolute value of negative 27 is positive 27. And we get 32.3 repeating units of space. So this plus this, right, in area. So that's what it looks like when we're just talking about area. This happens occasionally on homework, so you just have to be really conscientious about how things are worded. But now we're going to look at a lot of examples where we are talking about calculus, and we do need to consider that things are positive and negative and what that means for the overall picture. Okay. So for this example here, the figure below, f prime of t, shows the rate of change of f of t. So here, this is a derivative function that tells us the value, the rate of change of the value of an investment over a 5-month period. Okay, so f of t, the original function, is the investment, right? So if it's going up, that's great for us. If it's going down, not so great. This is the rate of change of that investment over 5 months. Okay, so we want to use the derivative to help us understand some things about the original function. So what are the things we want to know? During which months is the investment, f of t, so the original function, gaining value? During which months is the investment losing value? Can we use what we know about calculus to figure out during which month is the investment at a minimum? When is it sort of bottomed out? And then part D, during this 5-month period, does this investment make or lose money? Okay, so we're using everything we know about how derivatives relate back to the original function to try to answer these questions. So some of the stuff has to do with area. Some of it just has to do with things like positive, negative, increasing, decreasing. But we're sort of pulling it all together to analyze what's happening from this graph. Okay, so I'd like you to take 2.5 minutes, see what you can come up with for these 4 questions by using the information presented here, and then we will go through it together. Okay, take about 30 more seconds. All right. So for parts A and B, we are trying to use this derivative picture to tell us about the original function. So during which months is the investment gaining value? So if we had a graph of the investment, we know that it'll be gaining value if it's increasing, right? If the value is going up. And it'll be losing value if the function is decreasing or going down. So we need to figure out how that relates to our derivative. So as a reminder, if your derivative is positive or above the x-axis, then the original function will be increasing. So we're going to be gaining value from month 3 to month 5. So that's where the derivative is positive, which means that the original function is increasing. For part B, during which months is the investment losing value? That's going to be whenever the derivative function is negative. So from 0 to 3, our function is below the t-axis, so the function is negative, which tells us that the original function is decreasing or going in the downward direction, which is bad for investments. That means we're losing value. During which month is the investment at a minimum? So thinking about back in chapter 4, when we were looking for maxes and mins, we start by thinking about where we might have critical points. So critical points are where the first derivative equals 0. We see that happens in month 3. So we want to know, is that a minimum or a maximum? If it's a maximum, then we'll look at endpoints. But if it's a minimum, then we know we have like a U shape. So the way we look at this is we say, okay, we're going from negative to positive, which means that the original function is going from decreasing to increasing. And if it's going from decreasing to increasing, we know from the first derivative test that that is a minimum. So in month 3, our investment hits a minimum, okay? Now for part D, it wants to know during this 5-month period, does this investment make or lose money? So this is where the area comes in. Right? The area tells us how much the function increases or decreases. So if we look at the negative area, we can see that it's significantly bigger than the positive area, which means that we decreased more than we increased. So that means here we are going to be losing money over this 5 months. If the area above the x-axis was bigger, we would be gaining money. And if they were the same, if the area below was the same as the area above, that would mean we broke even. We didn't make money or lose money, but we are decreasing a lot more than we increased. And therefore we've lost money over that 5-month period. Okay. So that's how we evaluate that. And that's how we sort of think about contextually why we need both positive and negative area, because they're representing different things that can both happen in one scenario. Okay, so let's look at another example. This is just to help you think about how to set up integrals and how to think about the wording of different questions. So this ended up on 2 pages, so I'm just going to write the function on the top of the next page. So consider the function f of x equals x cubed minus 7x squared plus 11x. So this is the function that we are looking at here. We want to graph this function from 0 to 4. So we're interested in what's happening from 0 to 4. So we're going to graph it. And then we want to find the value for which this is going to cross through the x-axis. So again, we sort of saw some examples of, in the last one, it was a minimum, but it's where we change from positive area to negative area. So the places where we cross to the x-axis become important. So for part B, we want to consider the area that's above the x-axis. We want to set up an integral to represent the area above the x-axis and calculate that using our calculator. Then we want to consider area that's below the x-axis. We want to set the integral, calculate on the calculator. And then using B and C, we want to answer questions D and E. And so there's a slight difference in how they're worded. So we need to figure out how to use those values. For part D, we want to find the total area bounded by the function and the x-axis. So that's like example 1 that we did today. And then for part E, it says if capital F of x has a derivative of little f of x, use your answer from part B and C to find the total change from 0 to 4. So now we've put this in the context of calculus, and we want to use our answers accordingly. So try to do this on your calculator. You definitely need to graph it first. If you don't have a calculator, you can certainly pull up like Desmos or something on your phone to graph it, but you need a picture of what's going on here to be able to answer these questions. So I'm going to give you about 3.5 minutes. Since there's a lot of steps here, try it out, see what you can figure out, and then we will go through it together. Okay, take about 30 more seconds. All right. So we start with a graph of the function. So it looks roughly like this, where we have this positive area and then it kind of crosses through. And then if we stop at 4, it's kind of right where it's about turning around. So the first question was to find where we crossed through the x-axis. So we see that we only crossed through once, we didn't turn back around yet. So we want to find that intersection point. We can try to do it algebraically by seeing where the function equals 0, or if you've graphed it on a calculator, you can trace and find that point. But we get 2.382 approximately is where we crossed through. So that's what we're going to use to answer the rest of the questions, right? We need to know where we're positive, where we're negative. So that graph is what you're supposed to do in part A. So for part B, we're looking for the positive area, right? And so the positive area is the area that's above the x-axis. So we're looking for the area here. So we set up an integral. We have the integral from 0 to 2.382, right? So that's why we needed that point where we cross through the x-axis, because that helps us figure out what our bounds are going to be. And so now we plug in our function here, x cubed minus 7x squared plus 11x dx. When we put that all into the calculator, we get 7.719. So the positive area here is 7.719 by setting up our integral. Now, for part C, we want to get the area below the x-axis. So now we're looking at the area from 2.382 until 4. So remember that 4 was given as our upper bound because we were looking between 0 and 4 in the original setup. So we have 2.382 until 4. So we have x cubed minus 7x squared plus 11x dx. And if we plug that into the calculator, we get negative 5.053. So that's our negative area that we see in the picture. So now we need to think about how we use these areas, and it really depends on the question being asked. So for part D, we have a question that asks about the area between the function and the x-axis with no indication that we have derivatives or rates of change or anything like that. So we're asking how much space does this shape take up? So when we do that, we need to take the absolute value of all of our areas and add them together. So we're going to do 7.719 plus positive 5.053, because since we're not talking about, calculus, the amount of area this takes up is 5.053. So we add those together and we get 12.772. So that answers the question about area. For part E, we're told now that this is a derivative function and we want to use that to find the total change of the original function, which means now we are actually doing calculus and using the definite integral. So that means when we consider these two areas, we want to add them as is. So we go up by 7.719 in the original. That's how much we increase. And then plus negative 5.053, we decrease by 5.053, which means that our total change was 2.67. So when we do this with definite integrals, right, and we're doing it in calculus, we add these areas together as is, and this would be the same, part E, as if we did the full integral from 0 to 4 of x cubed minus 7x squared plus 11x dx, right? If we didn't split up into positive and negative, then we would get 2.67 because in the background, the calculator is assuming that you're doing definite integrals and total change and adds up the positive and negative area in the background. Okay. So that's how we step through and sort of really try to understand how to break things up. We're going to do one more example where we're using positive and negative areas. It's a really interesting problem. It's almost like a puzzle that I think is interesting, that is pretty common in sort of physics types problems here. Let's take a look at this one. So suppose a person is 50 miles away from their home. Okay, so you're already 50 miles away from their home and you're driving your car in a straight line. So you leave your house, you stay in your street, you just go straight. Their velocity is given in the graph below. So you can see that the t-axis is sort of right here in the middle, and that when you are going above the t-axis, you're moving away from home in the positive direction. And when you are below the t-axis, you're going back toward your home. So we want to use this information to try to figure out, when is this person farthest from their home and approximately how far away are they? When is this person closest to their home and approximately how far away are they? So are they 10 miles, 20 miles, how far away? And approximately how far did they travel over the 5-hour period? Okay, and we want to talk about their end position in relation to their home. So thinking about what's happening, I'm just going to draw a starting picture to help you sort of think about how to conceptualize this. There's a lot of different ways to do this. So if the visual helps, great. If you'd like to do another way, that's fine too, right? So our car here, we're starting 50 miles away from our house, right? And we're driving in this direction to start. Okay, so you want to think about, what does the positive area tell us? What does the negative area tell us? How can we answer these questions based on, the information that we're given in this picture? And just as a reminder, the axis is here, which is a little hard to see, right? Okay, so I'm going to give you about 3.5 minutes. See what you can figure out. If drawing a diagram helps, great. If it doesn't, don't worry about it. There's a lot of different ways to figure this out, but we are using information about the velocity, which is the derivative of position, to help us understand how far we go in each direction. Okay, so try it out, and then in a couple minutes, we will go through it together. Okay, take about 30 more seconds. Okay. So this one's a little tricky. There's a lot of different ways to approach this. So if you didn't do it the same way I did, but still came to the same conclusions, that's fine. I'm going to draw everything out. That's helpful for me, but you definitely don't have to do that if you don't want to. So we're trying to figure out where the car is, where this person is at different points in time, right? And we're looking over a 5-hour span. So I want to consider what's happening at these different time points. And so here, we're starting at time equals 0. We are 50 miles from home, okay? For the first 2 hours, right, we are still moving forward. We are still moving away from the home in a positive direction. So what my first step is to figure out how far we traveled in those 2 hours to see where we'll be after those 2 hours. Okay, so the way that I approximated this is I just used the shape of a triangle. This looks close enough to a triangle to me that I was like, okay, I can kind of approximate that way. So 1/2 base times height, right? I have half times 2 times 30. That gives me 30 miles. So that means, at time equals 2, right? I've gone, how do I want to put this? I've gone 30 miles this way, which means at that point in time, I've gone a total of 80 miles from my house. Okay, hopefully that makes sense. So here I'm 50 miles from my house at time equals 0. And at time equals 2, I'm 80 miles from my house because I've gone the 30 miles represented by this area. Okay, so then something happens, right? At time equals 2. At time equals 2, I see that I cross over from positive to negative, which means I'm going to turn around, right? So I'm going to kind of draw a little thing here to then go back in the other direction. So when I turn around, it's sort of like a U-turn, right? So now I'm heading towards my house for the next 3 hours. So let's look at what happens there. So over this 3 hours from time equals 2 to time equals 5, I get this area down here. So again, I'm going to approximate this with a triangle just because it's the easiest for me to look at here. If you didn't use a triangle and you approximated slightly differently, you should get something close to what I'm getting here. So 1/2 base, but now the height of my triangle is negative 60. Okay, so, oh, that's 3. From 2 to 5 is 3 hours. So 1/2, my base is 3 units from 2 to 5, and then my height is negative 60. Okay, so when I multiply these together, I get negative 90 miles. Now, the negative is the direction, right? So when it was positive, I was going away from the house. When it's negative, I'm going back towards the house. But remember, I was only 80 miles away from the house, and now I'm going to go 90 miles in the other direction, okay? So I'm going 90 miles in this direction, which means that where I am in time is going to look something like this. So at time equals 5, right? So at the very end of this trip, and I've gone all 90 miles this way, I am negative 10 miles from home. So I've passed my house and I've gone an additional 10 miles away from my house. right, at time equals 5. Because if I'd gone 80 and then I go back 90, right, that gives me negative 10. Hopefully that makes sense so far. So from this sort of first part of the diagram that we're going to have to put more information onto, we can answer part A. Okay, so part A says, when is this person farthest from their home and approximately how far away are they? So we have two extremes. We have the extreme where we're away from the home in this direction and the extreme where we're away from home in this direction. When we go in the first direction, we're 80 miles away from home. And when we go in this direction, we're 10 miles from home, right? So the 80 miles is certainly further away. So we know that at time equals 2 hours, we are the farthest away from home at 80 miles. So for part A, at hour 2, we are 80 miles away from home, okay? Part B says, when is this person closest to their home and approximately how far away are they? Well, we can see that we are literally going to drive right by our house, right? Like the how far away are they is 0 miles. So at the point we drive by, that's when we're closest to the house. So we really need to figure out when that happens, okay? And there's a lot of different ways to figure this out. I'm going to tell you how I did it. If you did it slightly different, that's fine. And we'll talk about what's a reasonable sort of situation here. So I'm going to try to figure out how far I went between time equals 4 and time equals 5. Okay, because I have a sneaking suspicion that that is going to be when this happens. And so I need to make sure that the area between 4 and 5 is more than 10 miles from the house. If it is, then I know that I have to pass between hour 4 and 5. So if I look at 4 and 5, I again have this little triangle situation that I can use. So my base from 4 to 5 is 1 unit. The height is negative 60, right? Can you guys all see that triangle here, right? So if I multiply that together, this gives me that this chunk of time is 30 miles from time equals 4 to time equals 5, okay? Well, that's more than 10 miles. So I know that from time 4 to 5, in between them is when I have to pass my house. Now, if this is 30 total miles and I've gone 10 miles in this little chunk, right? That means I've gone 20 miles here and 10 miles here, right? So I'm going to just set up as a proportion, right? So 30 total miles, 20 out of 30, right? 2 out of 3 is 0.6. So I'm going to approximate this to be 4.66, hour 4.66, which is 2/3 of the way between. Now, any answer that you get should be between 4 and 5. If you said 4.5, sure, you can definitely make an argument for that. 4.3, great. 4.7, great. But it's got to be between time equals 4 and time equals 5. Okay, that is something that for sure is true. And then the semantics of that just depends on how you're approximating, right? Anything between, I would say, like a 4.4 and a 4.7 is reasonable. Okay, so that's how I found this point. And so for part B, we're going to say time equals 4.66, and we are 0 miles from home because we are literally driving right by it. Okay, so for part C, approximately how far did this car travel over the 5-hour period, and explain their end position in relation to the house. So for the positive driving, from time equals 0 to time equals 2, this car drove 30 miles, right, in one direction. Then the car turned around, and from time equals 2 to time equals 5, we drove 90 miles in the other direction. So even though it was negative 90, right, is the approximation we have, that negative indicates a direction. So if we're talking about the total miles traveled over that 5 hours, it's 120 miles. So 30 miles in one direction and then 90 miles in another direction. So you can see why we would need to make that 90 positive to answer this question. Okay. The other part is explain their end position in relation to their home. So we've already talked about this a little bit, but they're going to be 10 miles away from their home in the other direction because they've gone 80 this way and then 90 back. So they are 10 miles past their home in the other direction than they started. Okay, so there's a lot of really good things happening here. Like I said, I like to draw a diagram to sort of understand what's happening, but you don't need to. You can certainly just work with the numbers and rationalize through it. There's a lot of different ways to think about this. So if you thought about it differently, but came to similar conclusions, then you are on the right track here. Okay. So that is our last example of positive negative area and why we would want to use them, how we might examine them, and how we can ask different types of questions to evaluate that. So the last sort of area type thing we need to talk about is how do we deal with area between curves, right? So all the area we've looked at so far has been area between the function and the x-axis. But now we want to ask the question, is there a way for us to talk about area between two functions, right? So just get the axis right out of there. So how do we do this? What does it look like? All that good stuff. So let's consider two functions here. We'll call this one f of x, and we'll call this one g of x. Okay. So just like before, we need to have bounds of where we're looking. So for the sake of the example, let's consider what's happening from 1 to 3, right? So let's say we're interested in the area between x equals 1 and x equals 3, okay? So that means that the area that we're looking for is this area right here, okay? That's what we want to ultimately get, but we don't know how to find that yet. So let's talk about what we do know, okay? If we were to integrate g of x from 1 to 3, right? That would give us the area underneath the g of x curve and the x-axis, like that, right? So it's this area down here. So we'll call that area A. If we were to find the area under the curve of f of x from 1 to 3, let's call that area B, that's going to be the area between the f function and the x-axis. Okay, so it's all this area here, that's area B. So if you were to take area B, all the red area, and subtract off area A, what you would be left with is the area between the curves. So that's our goal here, right? We want to take the area of the higher function minus the area of the lower function. So for this particular example, what that would look like, we would have the integral from 1 to 3, f of x, which is all this red area, minus g of x, which is the area underneath the blue curve, dx. So if we were to subtract those, it would leave us with the area between curves. And we can put it in one integral because it works a lot like derivatives where you can look at the area under one minus the area of the other and combine them together. Okay. So how do we write this in general? So in general, we have the integral from a to b of f of x minus g of x dx. I don't love this formula, and the reason I don't love it is because f of x and g of x are just sort of placeholders, and what we're really doing is the top function minus the bottom function, and there's no way to really say that within the formula. Most of the time, you're not even going to have f and g, you're going to have like y equals, and so you really want to make sure you think of it as top function minus bottom function. If we can take the area underneath the top function, subtract off the area from the bottom function, what's left is the area between the curves. Okay, so let's see what this looks like and let's see how we practice this. So for example 4, we want to find the area between y equals x plus 5 and y equals 2x plus 1 from x equals 0 and x equals 2. So whenever you're doing area between curves, it's a good idea to graph them So if you have the notes, the graphs are printed here. So these are the two functions that we're looking at. The blue is not as dark as I thought it would be. Right? So again, we have the function x plus 5 and 2x plus 1. And we're interested in what's happening between x equals 0 and x equals 2. So I'll write that up here. Okay, so what I would like you to do is set up an integral of the bounds, and we're going to do top function minus bottom function, and we're going to see what that area is. I'd also, if you don't have the graph, like you to sketch it and shade in the area that we're talking about. It's good practice for as these start to get harder. So take 2 minutes, try that out, and then we'll go through it together. Okay, take about 30 more seconds. All right. So if we look at the graph and we look at 0 to 2, we see that the area that we're interested in looks like this. Okay. And it's very clear which function is on top and which one's on bottom between 0 and 2. So when we set up our integral, we have the integral from 0 to 2, and we're going to do the top function, right, which is x plus 5, minus the bottom function, which is 2x plus 1. So again, we're going to want to use parentheses here because when you subtract off the function, you have to subtract off the entire function. So at this point, you can either enter it into your calculator like this with the parentheses, or you can simplify it first. Either is fine. So when you plug that into your calculator, we get an area of 6 between these two curves. Okay. So again, it's important that we know which function is on top and which function is on bottom so that we subtract them correctly. Otherwise, you're going to end up with negative area, which we don't want when we're talking about area between curves. Okay. So let's take a look at the next one. So find the area between the function 3x and x squared from -2 to +1. Okay, so this is what the picture looks like. If you don't have it there, you can sketch it, on your notebook. But what I want you to do again is I want you to shade in the area that we're looking for and think about what we might need to do to compute the area between curves. Okay, so this one's a little bit different than the first one. So think it through, think about what you're seeing, what you might need to do. I'm going to give you 2 minutes and then we'll go through it together. Okay, take about 30 more seconds. All right. So when we're thinking about the area from -2 to +1, something really interesting happens, right? We see that we get this like crossover moment right here at 0. So how do we deal with that? What do we do? Right? So the difference between what's happening before the intersection point and after is which function is on top, right? It switches. So we need to account for that. So that means that instead of doing one integral where we do top minus bottom, we have to do two because it changes. So the first integral is going to go from -2 to 0. So from -2 to 0, the function that's on top is x squared. So we have x squared minus 3x dx, right? So that's consistent, top minus bottom. We're going to get 8.667. But then something happens at 0. It switches, right? So from 0 to 1, we now need the 3x to be on top. So here we're going to have 3x minus x squared dx. And when we plug that in, we get 1.167. Okay. So notice that both of these are positive. When you do area between curves, it should come out as positive because we are talking about area and space here again, but using integrals to find it. We add these two together and we are going to get 9.834. Okay. I want to point out that there's another intersection point over here. So if we had been looking from say -2 to 8, we would have to have 3 integrals, one to represent this little part, one for this part, and then one once it's switched again. So that's why having the picture is so incredibly important, because we need to know when things change and when, like in the first example, it's consistent, right? The top function is always the top function between 0 and 2. But here, the top function changes on the interval we're looking at. And the only way we really would have seen that is with a picture, okay? So these two examples both give us bounds where we are looking. There's another type of area between curves where we don't have bounds. And so that adds another step that we need to do in order to figure out the area. So let's look at an example of that. So here, we want to find the area naturally bounded by 3x and x squared. Sometimes it says the word naturally, sometimes it just says bounded. And so what we're looking for, this is the same function we were looking at before, but now we're looking for a different area, right? So when we talk about an area bounded by two functions, we're looking for the area that's completely bounded. So it's closed off on all sides. So the area that we're looking for is this one right here, okay? Because if you pick any other space, it goes on forever in some direction. And so that won't work for us. So we are looking for the one that's completely bounded. So now, since we don't have bounds, our first step is to figure out where these two functions intersect, right, in terms of the x values, to find the bounds of our integral, okay? Once we find where they intersect, that gives us two intersection points. Those become the bounds of our integral, and then we can set up an integral top function minus bottom function. So we do have that extra step. So I'd like you to take 2.5 minutes. Again, the first step is to figure out where these two functions intersect to get your bounds, and then set up an integral with top function minus bottom function, right? And then you can plug it in, you can get that area, and in 2 minutes, we will go through that together. Okay, take about 30 more seconds. All right. So how do we find intersection points, right? This one is fairly straightforward, but they won't always be. So we want to make sure we know the process. There's two options here. So if you're graphing these on your calculator can find these intersection points for you. If you're not sure how to do that, you can Google the type of calculator you have plus graph plus intersection points, and it'll give you sort of the syntax of how to do that. If we want to look at this algebraically, we're answering the question, when are these two functions equal, right? Where they intersect is where they're equal. So we can figure out this algebraically. So if we subtract the 3x over to the left, we can then factor it. So we have x times x minus 3 equals 0. So we have two factors together equals 0. That means one of them has to be 0. So either x equals 0 or x equals 3. Those are the two solutions. And those are the places where we have intersection points. Okay, so you can always set the two functions equal, or you can graph the two functions. So that means when we're setting up our integral, we have an integral from 0 to 3. And now we need to do top function minus bottom function. So notice here that the linear function is on top. So that's our 3x minus the bottom function, which is our x squared function. So we have 3x minus x squared dx from 0 to 3. That's this little area that's completely enclosed. When we plug that into the calculator, we get that that area is 4.5 units. Okay, so when you see a question that says find the area bounded between this and this, if there's no x bounds given, that means that there's a natural enclosure. You should graph it, figure out the intersection points, and that will give you the bounds of the model. Okay, so we're gonna stop here for today. We're gonna do example 7 on Thursday. So as a reminder, your quiz is not till Sunday, but it'll be really helpful for you to do some of the homework on 5.3, specifically area between curves, before we tackle this particular problem, which is a little more advanced. So we'll start with example 7 on Thursday, and then we'll do 5.4, but definitely do some of the 5.3 homework before class on Thursday. Okay, have a great rest of your day, and I will see you all on Thursday.